Welcome back. We begin our third mini course. Giovanni Italiano will speak about building hyperbolic manifolds from Coxeter polytopes. Please welcome.
Thank you. Thank you for organizing this conference. Yes, I forgot the microphone. Okay. So this mini course will talk about building hyperbolic manifolds using polytopes instead of using number theory. It has its own advantages, its own shortcoming. We'll talk about that. But so we'll start with an introduction on Coxeter polytopes. We'll see how to use them to build a manifold. And then in the end, I wanted to do something that can share a more serious application, and I chose to do something about what I'm more familiar with. So we'll use these to build manifolds M, also, to construct and study maps from manifold M, hyperbolic manifold, to the circle S1 and study properties. This is related to the talk of Bruno of last week, for who was there. So I'll start with the usual definition just to fix the notation. For me, a hyperbolic manifold is a complete and finite volume Riemannian manifold with Riemannian manifold with constant sectional curvature. Sectional curvature always -1. So, except when I'm talking about the hyperbolic space, when I will say hyperbolic, I will always mean complete and finite volume. If I'm going to talk about something that has infinite volume, I'm going to specify that. So in the previous lecture, we've seen like a model, the hyperboloid model for the hyperbolic space. I'll briefly recall other two models which are more useful to visualize things, which are the half-space model and the Poincaré disk. So the half-space model of the hyperbolic space is simply we take the upper half-space of our n, let's say Rn. We take which with xn positive, and on it we put a metric which is, let's choose as a tensor, the hyperbolic is the size, okay, I guess. Yeah, okay. Which is proportional to the Euclidean one with this. So we're taking the upper half space, let's do this 3 space. We put here a different metric, and And for example, here vertical lines are going to be geodesic, but other lines are not going to be geodesic in this moment and in this model, and geodesics are more something like this. So arcs of circumferences that are orthogonal to the boundary. And the Poincaré disk is a disk, as the name suggests. So it's just, okay, no, I'll just call it dn. It's just the unit disk. And the tensor, the numbers are not important. We put another Riemannian tensor, which is so this at the point x is going to be again proportional to the Euclidean one. And let's draw a two-dimensional picture. Here in the, if you take H2 as D2, here to me the lines are going to be lines that go to the centers, so diameters, and arc or circumference that are orthogonal to the boundary again. So this is a line, this is also a line, but this is not a line. Okay, why do I care about this model? What do they have that is better than the others? Is the fact, you can see it here, that the tensor is just a multiple of the Euclidean one, so it's a conformal model. So the angles that you see in these models are actually the angles of the object you see. So if you see two lines and you measure this angle here, is exactly the angle that the hyperbolic metric measures. And since I'm going to talk about polytopes and angles, these are just a bit nicer. It's just a good way to represent hyperbolic space when we talk about this. So okay, so we go a bit. So this lesson is going to be very basic, just to introduce the topic. One question that we asked, Matthews asked in the last lecture was, does there exist a hyperbolic manifold of dimension n for every n? And this is like now a question that we answer with arithmetic methods, and okay, so sorry. So arithmetic methods are very powerful for this kind of question because they work in every dimension. Our methods will not work in every dimension that we can consider, but they can answer some other question like, does there exist a hyperbolic manifold such that and then we have some properties. For example, like with arithmetic methods, it's very, very hard to compute invariance of the manifold that you build. So for example, computing Betti numbers is like a very basic question, which is hard to do, hard to compute for hyperbolic for arithmetic manifolds built with arithmetic methods. You can, as I said before, defining maps from manifold and study them. There's some results you can obtain with, for example, with total geodesic submanifolds with arithmetic hyperbolic manifolds, but it's in general is harder to actually use the geometry and the topology of the manifold that you build. For example, other question you can find in even dimension. Let's say, okay, let's say it in general. Finding manifolds, hyperbolic manifolds with minimal volume. It's also something that can be attacked with the methods we are going to use. These methods are, so we are going to consider some pointopes, which are going to be the building blocks with which we will build the manifold and glue them in some way that is going to be very explicit. So once again, I'm going to start from the basic. I'm going to start with surfaces. So dimension 2. So if we consider just orientable closed surfaces, we know that there's the sphere S2, there's the torus, and then there's higher genus surfaces. And this admits a spherical metric, elliptic metric, with constant curvature 1. This admits a flat metric, constant 0, and all these are hyperbolic. So finding an elliptic metric on constant curvature 1 on a sphere is very simple. You just take the sphere inside R3 and you take the induced metric is going to be the one that you search for. If you want to look for a flat metric on the torus, I mean, you cannot just embed it in R3 and see the metric because there's going to be some curvature, and like the usual way to see it is either you see it as a quotient of Rn or you see it as a quotient of a square, which is the same thing. So this is the picture. Maybe I'll draw it here. So this is the picture that every person that cares a bit about math sees without even studying math. You just build a torus by quotienting opposite edges of a square. This is usually just used to see the torus topologically, but actually gives you a metric. Why does it give you a metric? Because the square has a flat metric, being a subset of the plane, and when you glue, this metric is going to be preserved. So just to compare with the Genus 2 surface. Also, the Genus 2 surface can be seen as a quotient of an octagon. You can just choose. Oh, let's do it this way. Maybe I should have used colors. Let's see if this works. Is it visible? Yes, more. Okay, let's try this. Is this better? Okay, I'll use the same color again. So why does this flat metric pass to the torus and the flat metric of this octagon doesn't pass to a Genus 2 surface? So, speak louder.
Angle.
Yes, exactly, angles. So here, let's do it precisely. Here inside the square, there's no issue of gluing because you're not gluing anything. When we are gluing two sides, we're gluing the square along. When you're gluing the square along the sides on a neighborhood of a point in the side, we just get two half planes, and so it's just going to be all right. And in the point, in the vertex, we get 4 90-degree angles that are exactly 2 pi. And so they just glue out perfectly. Instead, here we get many. How much is it? Is it 135? I don't know. It's like, I guess so. So we get these angles. If you follow through the vertices, they are all glued to the same vertex, because this one is the same as this one because they are on top of this edge, but it's also the same as this one because of this edge. But then is here behind this one is also this one, and if you follow through, this one for this edge is this one, but from this is this one, and from the top of this arrow is this one. So this is all the same, and all these angles are glued together, and so we get a point which has axis angle. So the sum of the angles is more than 2 pi, and so the metric does not glue nicely. Actually, this surface has a flat metric with one singular point, which is the vertex there. So this is actually how you can find a hyperbolic metric on the Genus 2 surface, because in the hyperbolic plane there is an octagon which has angles of 45 degrees. So you just take this octagon, which I'm drawing horribly. So in H2, there is an octagon with angles pi over 4, and when they are all around the vertex, when we glue, we get angle 8 times, because there are 8 around the vertex. We see the octagon 8 times pi over 4, which is exactly 2 pi, which is the right amount. Okay, so let's find some exercises. So exercise 1, prove that every SG with G at least 2 has a hyperbolic metric. And maybe exercise 2, which is a bit, less direct. So we draw a genus 3 surface. Let's do yellow. Let's see if it works. It looks like it's working. So, is there a genus 3 surface such that the yellow curve is a geodesic of length, I don't know, 2025. No, this is a bad color. Let's do it like this. And if we also want length of orange equal to, I don't know, e to the pi, so maybe we'll talk about it after in some exercise sessions, just to see that you can actually have some flexibility and have some controls also on the geometry of the things you build. Okay. So polytopes, what are they? So polytopes are just the generalization of polygon and polyhedra in dimension n. So we fix a space, let's say x. X could be Sn, Rn, or Hn, the hyperbolic space. Everything that I'm going to say now is going to work in all 3 spaces, which with some differences, which is based on the geometry of the spaces, of course. But like the general facts work everywhere. So, okay, let's first say, so if I take a hyperplane in one of these spaces, it separates x into 2 2 parts we call half space. And so a polytope to me P to me is just locally finite intersection of half spaces with finite volume. Okay, and let's say that a polytope is finite. If it is the convex hull of a finite number of vertices. So here there is a bit of a difference in that arises in the hyperbolic space. So in Sn, and I mean, Sn is compact, but also in Rn, a polytope to be finite volume, it has to be compact. In Hn, this is not true. A polytope can have vertices at infinity and still maintain finite volume. For example, in H2, one can take a triangle which is just the intersection of, like, let's see, like these three half spaces. So this is a triangle, and this triangle actually has area pi. So we are going to talk about faces of polytopes. That are actually the part of the polytope which is in this, in the hyperplane. So we are going to talk about d-dimensional faces. So combinatorially, I see the polytope. I can also see the polytope as a poset of its faces. So a polytope has its facets to me. So a polytope P inside a space of dimension n, I will call a facet a n-1 face of the polytope. I will call a vertex a 0 face, which is just a point, and I will call an edge a 1 face, which is just going to be a line, which is a geodesic. And sometimes I will call a ridge an n-2 face. So as I was studying before, in the hyperbolic case, vertices can be real or ideal. So a real vertex is a vertex that's actually inside Hn, and an ideal vertex It's not in HN, but it's in the boundary of HN. So the polytope actually, that vertex, I think about it combinatorially, but geometrically it's not there. It's not it's not part of the polytope. So the boundary of the polytope is just homomorphic S to Sn minus 1 minus the ideal vertices. And the set of facets is an affine complex on this space. Okay.
So in your terminology, is an ideal triangle finite?
Yes.
So isn't every polytope?
Okay, no, so no, sorry. I'm just, yeah. Yeah, in X, let's say. Okay. Yeah, thank you. Okay, some examples just to be pedantic. You can have both ideal and real vertices. For example, you can have a triangle like this. Oh, this line continues. You can have only ideal, you can have only real vertices. You can you can have more have examples in higher dimension, which I'm gonna make. I'm gonna take a little time to talk about regular polytopes, just to. So regular polytopes are polytopes, to me, are polytopes where all the facets are isometric. And there's actually an isometry that sends every facet, sends the polytope in itself and every facet to is transitive on the facets. The isometric group is transitive on the facets. So how many regular polytopes are in every dimension? In dimension 2, so here we're not yet talking about geometry. I'm just talking about polytopes in Rn if you want. They can be represented in all three spaces, be like this. So in dimension 2, there's an n-gon which is regular for every n. Dimension 3, we have the Platonic solids. No, we have the simplex, which is just a tetrahedron, the cube, and the octahedron. And we also have the dodecahedron, which has 12 facets, which are pentagons. And then there's the icosahedron, which has 20 facets, which are triangles, equilateral triangles. An octahedron has 8 facets, and they are triangles. So in general, before I talk about dimension 4, in every dimension there are at least 3. There's the simplex, there's the hypercube, and there's the octahedron. How do we know this? we always have the simplex. We always have the hypercube, and we always have the, let's say, hypercube. We always have a and they always exist because, for example, the cube is the ball in norm L infinity, the hyperoctahedron is the ball in norm L1, and the simplex is a face of the hyperoctahedron of dimension 1 more. And actually, when the dimension is higher than is at least 5, these are the only 3 that exist. In dimension 4, the situation is similar to dimension 3, except there is 1 more. So we have the correspondent to this 5, and then we have 1 more. So we have the simplex, the cube, then there's the hypercube, the hyperoctahedra, and we have the so-called 120 cell, which is a polytope that has 120 facets, which are all dodecahedra. And then there's the 600 cell, which has 600 facets that are like the icosahedron. And then there's the last one, which is the 24 cell. Just 24 facets that are, there are octahedra, it has 24 of them. So one thing that maybe is useful to acknowledge is that polytopes can be dual to each other. For example, the cube and the octahedron are dual polytopes. So if I draw a cube, and what does it mean to take the dual? It means that I just reverse dimension and codimension. So for every thing in dimension 2, I'll write something in dimension. So this is left, right, down, up, front, and back. I draw 1 vertex for every face, and then every time 2 faces are adjacent, I draw an edge. So here we get dual to the cube, we get the 1 skeleton of the octahedron, and then when I glue 1 face for every vertex, I just get the octahedron. So you can actually see this every time. The simplex is always self-dual. Cube and octahedron are always dual to each other. Icosahedron and dodecahedron are dual to each other, and the 24 cell is self-dual. Okay. So I've been talking about only the combinatorial issues about this, the combinatorial properties of these polytopes for now, while we actually care about the geometry of them to see which, so in to see how they can be realized inside these spaces, which angles could they have, something like this. So what's the dihedral? I'm unable to. So every time I have a polytope inside space, and I have 2 facets two facets are adjacent. Then there is a dihedral angle between them. And I care about these angles because when we were gluing polytopes before in dimension 2, we needed to be careful that when we glue along around the point, the sum of the angles is exactly 2 pi, and we translation of this condition in dimension n is going to be to talk about these angles. So I'll just give a definition and then we'll have a quick pause to what is a Coxeter polytope. Okay, so is a polytope P such that all are pi over an integer. Possibly different, let's say, natural. Possibly a different integer for every angle, but I want all angles to be submultiple of pi. I think I'm gonna stop now for a second and then we'll get in 5-10 minutes. Are there any questions? I know it's started slowly.
Is now all the angles that enough to reconstruct?
Sorry, can you repeat?
Isn't knowing the angles enough to reconstruct a polytope up to scale?
We are going to talk about that. In particular, Coxeter polytopes are not going to exist always. And in fact, when the dimension is high enough, they don't exist at all. So it's like, yeah. So
If there exists, you can say
you can say, sorry?
Yeah, but if there exists a polytope that's given dihedral angles, is it unique? Up to scale?
So it depends on the things you say. No, in the Euclidean space, it's not true. No, because you have. Yeah, the question is like if you fix the angles, is the polytope unique or not? Like it depends on where. Like in Euclidean space, you can just take a rectangle and a square. They have the same angles, and they don't even. In hyperbolic space, at least in hyperbolic 3 space, it's true. I think it's possibly true also in higher dimensional. I'm not sure. Yeah, okay. If they're not obtuse, it should be, yeah. Okay, I think we can start again. Okay. Okay, first let me make a correction because it was pointed out that I gave a definition in a rush and it's wrong. So regular polytopes, it's just the isometries act transitively on flags. You need not only on the facet. If you just fix a facet and minus 2-dimensional and a minus 1, and you fix another one, then there's an isometry that sends the polytope to itself and the first flag to the second one. Okay, so we go back to Coxeter polytopes, and they are connected to Coxeter groups. So what happens if you take a Coxeter polytope, P, and you call maybe F1, Fm is facets, maybe M, I don't like it, Fr, and then let's say that Mij is the angle, let's say that angle between Fi and Fj is pi over Mij. So every facet corresponds to a hyperplane in the hyperbolic space. And so we can associate to it the reflection Ri, which is the reflection along hyperplane defining Fi. And we can consider the group generated by all the reflection along the facets. So G is group generated by Ri's, and the relations are going to be first one, that when you do a reflection twice, you just get the identity. And the second one is what happens when you do two reflections along two different facets, and you get this relation. This is called Coxeter group. The one associated to the polytope, and it actually can be seen as a subgroup of the isometries over space X, which soon is going to be the hyperbolic space if we want to consider hyperbolic polytopes. But in principle could be
Why it is injected?
because the reflections are isometries of the, because we are considering,
It's mapped to isometries, but why there are no kernel?
okay, because because I'm claiming that these relations are the kernel, if you want. So the point is that G acts on our space, and the action is proper, and the quotient is actually the polytope P. So in some sense, this tells us that from polytopes we can build manifolds, because we can always build a manifold from a Coxeter polytope because of the Selberg lemma that was mentioned also more or less an hour ago. That when we find G which is a lattice, we can also find a subgroup which is finite index and torsion free. So in other words, if G acts by isometries properly, and let's add the finite covolume. Then there is a subgroup of finite index that acts freely. And so this is on HN, let's say. So, so the quotient HN mod G prime is a hyperbolic manifold. So the idea is that this, this is very obscure. No, it's not giving us this subgroup. It's not giving us anything. It's just telling us that it exists. But in principle, every time you build a Coxeter polytope, you can have a manifold. It can be enormous. There's been a lot of copies of the polytope. We are not guaranteeing anything else other than existence. So in some sense, another geometric way to see this is for people that know what it is. P can be seen as an orbifold. And our manifold M just is just a covering space for our orbifold. There's many invariants that we can just compute for the polytope and then pass to the manifold M. For example, one could define Euler characteristic for polytopes, which is just going to be something like we do for every phase, we do the alternating sum of the dimension, but we have to divide by some cardinality of the stabilizer. So we just, this here is the cardinality of the stabilizer of the group of the phase F by the action of the group G. Okay, so yes, so the manifold we are building covers the polytope and is actually tessellated in some copies of the polytope. But we want to do this explicitly. Maybe some yes, let's say this just as a curiosity. So when the angles are non-obtuse, which is always the case for a Coxeter polytope, unless we are considering angle pi in some weird spherical thing, then the polytope is simple. Which means that we never have something like, let's do a proof by, like a definition by non-example. So, no, this is horrible. This is an octahedron. In an octahedron you have facets that are touching, but not in only in a vertex. No, these two opposite facets here. A simple polytope is exactly one where when two faces intersect, two d-dimensional faces intersect, they intersect in a d-1 dimensional one. Okay, just some other terminology about Coxeter polytopes, because I don't think we are going to use it in the future, but it's quite standard and very much. Like the octahedron is not, because this vertex, these two facets intersect in a vertex. Or, for example, the icosahedron, if you have a picture in mind, you have 5 triangles that glue in a vertex. And so this example is purposely confusing because actually
Cube is not simple too.
why? A cube is simple.
Two opposite.
Okay, if they intersect, then they intersect. Yeah, that's, yeah. So let's talk about Coxeter diagrams just briefly. So these are just a way to encode the information of a Coxeter polytope. So these are graphs. So vertices correspond to facets, and edges that will be labeled will correspond either to angles between facets, will correspond to the intersection of the facet, the nature of the intersection between the two facets that are the vertices, so are angles or some other label for non-intersecting. So in particular, there's weird conventions to just not. So the diagram is going to be a vertex for every facet, and we are supposed to put an edge for every pair of facets that tells us whether the two facets are intersecting, and if yes, at what angle. But, so there's some notation. So we write if the angle is pi over m. We write m over the arc, but we ignore the edge of the, but we, okay, I need more space. No, if the if they are parallel, we put a bold edge if the facets do not intersect, not even at infinity. We put a dotted line. And also, just to complicate things, we do not write the edge at all if m is 2. And we usually do not write the number if m is 3. So for example, this Coxeter diagram would mean that this is a 3 and this is actually a 2. So this would be a spherical triangle with angles 2, 3, and 4. For example, if we wanted to write a Coxeter diagram for this no, let's make it, let's take this quadrilateral where the angles are 0 because this point is ideal. This is maybe pi over 6, and this is pi over 7, and this is pi over 2. We would write 4 vertices for every facet, 4 vertices, 1 for each facet. Then these 2 facets correspond to these 2 vertices. They are parallel because they meet at infinity. So this here there is a bold edge. These 2 do not meet, so this is dotted, this is dotted. This will have a 6 written over it, this will have a 7, and this should have a 2, but I will not write it. Because usually there's, so the reason for this is that usually there's many 2s and many 3s, and so it's a way to save space and make it legible. And sometimes you can find in the literature, instead of writing 4, you can find a double edge. Instead of writing 5, there's a triple edge. Instead of writing 6, 4 edges. And then people stop putting so many edges.
What do you mean by parallel specifically?
Okay, so
Because
yeah, this is like a,
we're considering when they meet infinity as parallel.
yes, because in the hyperbolic space, there's this phenomenon that can happen. Now, the 2 lines can be either intersecting, in the Euclidean space, 2 lines can be either intersecting or parallel. In the hyperbolic space, there's actually 3 possibilities. They could intersect, they could be ultra-parallel, or they could be parallel, which means that they just go to the same point at infinity. That's this.
The later 2 ones are parallel.
So
Or just in
these are parallel. These are not. These are what's sometimes called ultra-parallel. So to go back to a question before, you can read many things from these Coxeter diagrams. So you can basically, if it exists, you can reconstruct the polytope. So you can you can read, for example, what are the so let's say first this one. So there's a result Coxeter. I think it's 1934. There's a complete classification of the spherical and the Euclidean Coxeter polytopes.
Again, a cube,
Hmm?
people would have the same box to
Yes, yes. They're not necessarily unique, but the classification. Let's say it's the so there's actually more data that you can add to this, and talk also about distances between facets that do not touch with each other, and this should help you recover also this case. But so my point now is like that there is a finite list of things that are spherical and Euclidean, I mean, of building blocks, which like all connected Coxeter diagrams that are realizable in the spherical and Euclidean plane are classified. So there's a finite list. For example, if you take the product of two, you take a polytope in R4 and a polytope in R3, and you can take the product. These are going to be disconnected because everything is going to be orthogonal to each other, and so you can actually. There's polytopes outside that, but this finite list helps you recover something on the polytope. For example, to find faces of P, for example, they correspond to spherical subdiagrams. Of your diagram. So I guess what I'm trying to argue is that this combinatorial data tells you a lot more than what it looks. It doesn't just tell you that. Maybe this is also imprecise because there's ideal vertices they will correspond to parabolic subdiagrams and etc. And so I guess I need to say something yet. I think I deleted the picture. No, let's finish by making a list of some Coxeter polytopes. So which I'm a bit late. So which regular are, let's say, realizable as 2 pi over an integer, because I have some lists, and sometimes it's also useful to say it like that. So okay, in dimension 2, there's so the in the hyperbolic space. So the magic of the hyperbolic space is that you can take a Euclidean polytope, just put it on the tangent and push it on the hyperbolic space, and then just continue pushing until you meet the infinity. And the angles start very, very close to the Euclidean ones, and then just go, just reach a limit at infinity. In dimension 2, you can realize everything between the Euclidean angle, which you cannot, and 0 at infinity. So actually you can realize if n, so a triangle, you can realize it as pi over 4, pi over 5, etc. Square, pi over 3, etc. And all else you can realize with every Coxeter angle. Dimension 3, let's make a table. So we have the tetrahedron, we have the cube, we have the octahedron, we have dodecahedron, and we have the icosahedron. I'll write here the Euclidean angle. And the Euclidean angle is going to be around 70 for the tetrahedron, 90 for the cube. This should be like around 109, around 138. So let's say some angles like pi over 3, pi over 2, no, let's say 2 pi over 5 first. Pi over 2, 2 pi over 3. Okay, so the tetrahedron can be realized as a spherical polyhedron here and as an ideal polyhedron in H3. So it has much flexibility on the angles you can choose.
What do you mean by spherical?
I mean that you can find a Coxeter tetrahedron inside S3. So you can just define in S3 as you define in H3 with the intersection of this, and you can find all these angles because these are angles that are more than in the spherical. Then it's going to be the opposite of the hyperbolic geometry. You just increase. So a cube you can realize in the Euclidean space with pi over 2, and actually you can find an ideal cube in H3. You can find this measure in S3 and this one in S3. Interesting facts or like interesting polytopes are the octahedron and the dodecahedron. So the dodecahedron can be realized as ideal in H3 with right angles, and the dodecahedron can be realized in H3 with right angles as a compact compact polytope. I don't care much about all the other angles, but let me finish. So like this is the ideal dodecahedron has pi/3 in H3. So here you still will get H3. Here is going to be S3. And yeah, this is just S3 because it's 2 pi/3. It should be more than this. Okay, so what's the catch here? So we can build manifolds, interesting hyperbolic manifolds, using all the time where H3 appears here, especially with right angles that are going to be very easy to use, and also here if we want. But so let me just say a couple of words on something that was.
Icosahedron does not occur in any of this?
The icosahedron. So one thing that's interesting is what I was going to. The icosahedron, like the octahedron, they're not simple polytopes. So they should not be realizable with acute angles. And in fact, so the icosahedron can be realized here in H3. But in fact, the thing that was weird that I was almost going to point out is that this has not obtuse angles, but is simple. But is not simple. And this is due to the fact that in the ideal picture, the vertex is at infinity. So here, this is not a simple polytope, but it's not an issue because the point at infinity is not there. So yeah, so when yes, I guess I'm late with the schedule, so I cannot talk really about regular polytopes in dimension 4 and polytopes in general. I'm going to talk about them tomorrow. So I'll finish here.